Welcome back to this lecture of EV batteries. In this lecture we are going to take a look inside the battery to understand what microscopic parameters determine the battery performance. Let's consider the atomic scale working of lithium-ion battery by looking at the classical combination of the graphite negative electrode with lithium cobalt oxide or LCO positive electrode as commercialized in 1991. Lithium can be stored between the graphene layers in the graphite and in the interlayers of the cobalt oxide host, or short for LCO. Lithium is relatively weak bond in graphite, the negative electrode, compared to the LCO, the positive electrode. The resultant chemical driving force for lithium to move from the graphite toward the LCO expresses itself as the battery voltage. This driving force will cause the battery to discharge spontaneously, but only if the lithium ions are allowed to move through the electrolyte from the negative to the positive electrode. The electrolyte only allows passage of lithium ions positively charged lithium. Therefore, this charging requires the electrons to go through the external circuit. Only when the external circuit is closed via an application, an electrical current will run, driven by the lithium ions that migrate from the negative to the positive electrode. Under these conditions, the battery is discharging. During discharge, the negative electrode produces electrons corresponding to oxidation of the graphite, in which case the negative electrode is called anode. At the positive electrode, electrons are consumed, which corresponds to reduction, in which case the positive electrode is called cathode. Charging the battery is achieved by applying a current opposite to discharging, which requires a voltage larger than the battery open circuit voltage. This will drive the electrons back from the positive to the negative electrode via external circuit, and thereby also the lithium ions. In this case, electron production and consumption are reversed, and thus also the anode-cathode assignment switches between discharge and charge, as opposed to the negative-positive electrode assignment that remains the same. Now we are going to relate the atomic scale properties of electrode materials to the microscopic performance parameters. Let's start with capacity, voltage, and energy density. The chemical reactions that occur in batteries involve electron transfer, which are called redox reactions, referring to reduction and oxidation. From the battery redox reductions, we can calculate the capacities of the electrodes. Here you see the redox reactions at both electrodes, which to the right represents discharging of the battery. These are called insertion reactions because the lithium ions are inserted into a host material at the negative and positive electrode as the battery charges and discharges respectively. The approach of calculating the electrode capacities and the battery energy density is as follows. Imagine we need to store 1 mole of lithium ions. Then the capacity equals Faraday's constant 96,500 Coulomb. To store this capacity in the lithium ion battery, we can determine the amount of moles of electrode materials from the redox reactions, and from this their mass of the electrodes. The capacity divided by the weight of the electrodes is the specific capacity. Because the anode and cathode generally have a different specific capacity, the masses of the anode and the cathode will be different. Remember that energy density is the capacity times the average voltage. Therefore, the theoretical energy density of the combination of the two electrodes equal the capacity times the average voltage divided by the total mass of the two electrode materials. The practical energy density of the entire battery is much smaller, roughly around 30% of the theoretical energy density, because of the weight of the non-active materials including the electrolyte, current collectors, and packaging. Both the specific capacities and average potential of existing electrode materials are known, making it possible to calculate the energy density of any combination of electrodes. The potential of electrode materials is typically referenced to that of lithium metal. The lithium metal potential is conventionally set to 0 as reference potential, which has no consequence because the battery voltage is always the difference between electrode potentials. Next, let's have a look at what determines the internal resistance and power density, which determines, for instance, the charging time of the batteries. As a result of the battery internal resistance, the battery voltage increases with the charge current. It decreases with discharge current, as we have seen in the previous lecture. As a consequence, the energy efficiency reduces with increasing current, and as a consequence, more heat is produced in the battery. Looking into the batteries, there are four main contributions to the internal resistance: lithium-ion conduction through the electrolyte, charge transfer of the lithium ions toward or from the electrode material, lithium-ion conduction through the electrode material, and finally, electron conductivity between the electrode material and the current collector. In many cases, lithium-ion transport through the electrolyte in the pores of the electrodes dominates the internal resistance, and therefore determines the charge and discharge time and the power density. A way to improve the lithium-ion transport through the electrolyte that fills the pores of the electrode is to make the electrodes more porous. However, that decreases the amount of electrode material, which lowers the specific capacity of the electrode. This effectively lowers the battery energy density, as the same weight of current collectors, separator, and packaging are required. Another strategy is to make electrodes thinner, but also that results in less electrode material and hence in lower energy density. Effectively, both strategies will increase the power density, leading to shorter charging times, but at the expense of energy density, demonstrating the trade-off between power density and energy density. As a consequence, the lithium-ion battery designed to have a higher power density will have thinner electrodes as compared to that designed for higher energy density. Next, we consider potential causes of finite cycle life of batteries, that is, limited amount of times they can be charged and discharged. The electrolyte in the battery is exposed to the reduction and oxidation potentials of the two electrodes. If the electrolyte is oxidized or reduced by these potentials, this implies that the electrolyte is decomposed into another species, which may be insoluble in the electrolyte, often bonding lithium in such a way that is not active anymore. As a consequence, some capacity is irreversibly lost and part of the electrolyte is decomposed, which are major factors that cause a finite battery cycle life. For the large voltage of lithium-ion batteries, stable organic electrolyte have been developed. By mapping the electrolyte stability window on the potentials of the electrodes, we can determine which electrodes fall within the electrolyte stability window. However, it is not always necessary to have electrode potentials within the stability window to achieve a long cycle life. Looking at graphite, the potential below what existing electrolytes allow, hence the graphite negative electrode will reduce the electrolyte. Nevertheless, graphite is the most applied negative electrode in lithium-ion batteries. How does this work? Depending on the electrolyte, its reduction leads to solid electrolyte decomposition products on top of the graphite surface. This film is known as solid electrolyte interface, or SEI. The SEI should not conduct electrons to protect the rest of the electrolyte from the graphite electrode potential. In that case, electrolyte decomposition is pacified, similar to the thin aluminum oxygen layer that prevents to oxidize further when exposed to air. The SEI should conduct lithium ions, allowing the necessary lithium ion transport during battery charge and discharge. Electrolytes are optimized to form stable electronic insulation and lithium ion conducting SEI, aiming at a long battery cycle life. Another aspect that can lower the cycle life of lithium-ion batteries is the repeated volume changes of the electrode upon the lithium insertion and extraction during battery cycling. During cycling, this may result in cracks in the electrode material. As a consequence, the electrode material may become isolated from the current collector and thereby inactive, resulting in capacity loss over cycling. Depending on the specific electrode material, large structure changes typically play an important role in the cycle life of lithium-ion batteries. Also, the operation conditions of lithium-ion batteries have a large impact on the battery cycle life. High temperatures enhances electrolyte decomposition, which, as discussed, is determinant for the cycle life. High temperatures can occur due to outside temperature, but also because of heat development in the battery due to internal resistance. This might require active cooling to guarantee a longer cycle life. Lower temperatures increases the internal resistance, which effectively lowers the power and energy density of the batteries, but only when kept at lower temperature. Batteries of electric vehicles consist of many interconnected cells in combination forming a battery pack. To secure a long cycle life, safety and optimal performance of current and capacity distribution over the individual cells needs to be regulated. This is achieved by Electronic Battery Management System, the BMS. The BMS continuously monitors the voltage, state of charge, and the current of the individual cells in the battery pack and is able to regulate how individual cells are charged and discharged. One of the important rules of the BMS is to balance the state of charge of the individual cells. This is to prevent individual cells to be at a relatively high or low state of charge, which exposes the electrolyte to relatively large overpotentials. As discussed, this may lead to electrolyte degradation, one of the major contributions that shorten the cycle life. There are several ways to achieve balancing, where a sophisticated approach is to shovel the energy from the higher charged cells to the least charged cells. In this way, the BMS is vital to achieve a long cycle life of the battery pack in combination with providing optimal performance. Hereby, we have reached the end of the battery lectures. I hope they helped you to gain insight in the working of EV batteries.